Welcome back, everyone. I am absolutely thrilled to have you here for today's explainer. Today, we're looking at something you're probably surrounded by at this very moment, something so completely ubiquitous that it just fades into the background of our daily lives. I'm talking about concrete. But we aren't just looking at standard concrete today. Oh no. We are going to unpack the invisible chemical revolution that literally shifted the boundaries of modern architecture and engineering. Because without this microscopic intervention, the massive modern megastructures, the soaring skyscrapers, and those deep subterranean transit systems we all rely on, they simply could not exist. No way. So get ready, because we are about to shrink way, way down to the nanoscale to understand the hidden science holding up our world. Here is a quick look at our roadmap for today. 1. The concrete water paradox. 2. Enter the superplasticizers. 3. Mechanisms, specifically repelling the particles. 4. The super effects. And finally, 5. Building the modern world. Let's jump in. Section 1. The concrete water paradox. The builder's ancient dilemma.
For centuries, engineers and builders have wrestled with this fundamental conflict baked right into the very recipe of concrete. It comes down to this: how do we build colossal skyscrapers when the very water needed to pour the concrete is exactly what weakens it? Think about that for a second. To get concrete where it needs to go, pushed up a massive pump, squeezed through dense webs of steel rebar, and poured into complex molds, it needs to flow easily, right? It needs water. But here's the kicker. Water is the absolute enemy of final structural strength.
So the crucial point is this intense balancing act. If you use a high water-to-cement ratio, while the mix is highly workable, it flows beautifully. But as that excess water eventually evaporates, it leaves behind all these microscopic voids, making the final cured concrete weak and porous. Now, conversely, if you use a really low amount of water, you get incredibly strong, dense concrete. But there's a major catch. It's thick, it's stiff, and it is practically unpourable. For a very long time, the entire construction industry was basically trapped between these two opposing realities. You literally couldn't have both. Section 2. Enter the superplasticizers, the hero of the mix. In the 1970s, everything changed when we found a way to essentially cheat the paradox. Superplasticizers, or if you want to get technical, high-range water-reducing admixtures, HRWRs for short, are these highly sophisticated chemical additives that you pour directly into the concrete batch. And their primary function? They dramatically reduce the amount of water required in a mixture, while miraculously maintaining extreme fluidity. It's a real game changer. This means you can finally get the incredible strength of a low water mix, but with the easy workability of a high water mix. And when I say they dramatically reduce the water, I really mean it. By adding these admixtures, engineers can slash the water content in a concrete mix by a staggering 25 to 40%. To put that into perspective, that single metric fundamentally alters the physical properties of our most used building material. It's what allows for the production of incredibly dense, high-strength concrete that can still be effortlessly pumped hundreds of feet straight up into the air. Section 3. Mechanisms. Repelling the particles. A microscopic battle. Okay, let's dive into this. How exactly do these chemicals pull off this magic trick? Well, when you mix normal cement particles with water, their mixed positive and negative surface charges cause them to instantly attract. They crash into one another, coalescing into these tightly packed flocks. It's like they're huddling together. And these clumps physically trap a considerable amount of the mixing water inside them, which utterly ruins the fluidity of the whole system. But introduce the superplasticizer, and it violently breaks up those flocks. It releases the trapped water, leaving freely dispersed, evenly spread particles. Now, different generations of superplasticizers actually achieve this using two distinct mechanisms. Older admixtures, like SNF or SMF, use what's called electrostatic repulsion. They chemically attach to the cement and impart a strong negative charge, forcing the particles to violently repel each other. It's exactly like trying to push the negative ends of two magnets together. They just won't touch. On the other hand, newer PCE admixtures use steric stabilization. These molecules have this fascinating comb-like structure where long, flexible polymer chains stick out into the water. These chains act like combs that won't tangle, physically blocking neighboring cement particles from getting close enough for their natural attractive forces to take over. And this brilliantly illustrates the whole process, which happens in just a fraction of a second. Step 1. The admixture chemically attaches to the calcium ions right on the cement grain. Step 2.
the repulsive mechanism fires up, so either those negative electrostatic charges deploy or those long polymer chains extend outward. And then, step 3, the cement grains are violently forced apart because the attractive forces are now completely overwhelmed. The particles smoothly slip past each other without sticking at points of contact. So the fully dispersed cement completely loses its yield strength and suddenly acts as a smooth flowing liquid.
Section 4. The super effects, balancing the trade-offs. So we've seen the chemistry, but what does this actually mean out on the construction site? Well, while these chemicals are incredible, they aren't magic dust. They require very precise engineering. Looking at the advantages, sure, we see a massive increase in workability, a rapid rate of early strength development, and drastically reduced permeability, because, remember, we've removed all that excess water. But there are real trade-offs. Economically, popular superplasticizer brands run anywhere from 100 to 120 rupees per liter in markets like India, which definitely adds upfront admixture costs to the project. Technically, they can cause a much greater rate of slump loss, meaning the concrete might lose its workability faster than a normal mix would. Furthermore, if you overdose the mix, you risk severe setting delays or even segregation, where all the heavy aggregates just sink right to the bottom. It requires an absolutely perfectly balanced recipe. Section 5. Building the modern world, from nanoscale to megascale. Let's move to and see how this builds the world around us. Going straight from the chemistry lab to the modern skyline, the applications here are totally world-changing. Because we can now produce flowing concrete with very low water content, this is the exact technology used to pump high-strength concrete hundreds of meters straight up into the air to cast the cores of modern skyscrapers. It's heavily utilized in massive infrastructure developments too. Think of the sprawling metro projects, the tunnels, and the bridges currently transforming cities like Mumbai, Bangalore, and the Delhi NCR. It's also the hidden secret behind those highly durable precast concrete elements you always see being transported down the highway. Because of these chemicals, they can achieve incredibly high early strength, allowing factories to just pop them out of their molds in less than 24 hours. But perhaps the most profound impact of all of this is durability. I want to highlight this quote directly from the source material. It says, "Durable concrete mixtures are now being used in the construction of marine concrete structures for a service life of 100 to 150 years. To really put that into perspective for a second, conventional concrete structures in those harsh, salty environments often only have a service life of about 40 to 50 years. By using superplasticizers to drop the water content, we make the concrete so incredibly dense and impermeable that corrosive chemicals simply cannot penetrate it. We are literally tripling the lifespan of our most critical infrastructure." It really makes you look at the city's skyline entirely differently, doesn't it? Knowing that the soaring height and the century-spanning durability of modern cities are directly dictated by microscopic polymer chains acting like tiny combs and magnets. So how will these invisible chemical bonds construct our future? As we demand taller buildings and greener, much longer-lasting infrastructure, the answer is undoubtedly going to lie not just in how much steel and cement we use, but in the invisible chemistry happening right there at the nanometer scale. Thank you so much for joining me on this explainer today. Keep asking questions, and I will see you next time.